because if we take an EKG, there's two reasons this matters. If we take an EKG, it's going to cause ST abnormalities. It could also cause long QT. If we look at a normal EKG, and I'm not real good at drawing these, we label these. This is the P, this is the Q, this is the R, this is the S, and this is the T wave. And what I wanted to point out is this area out here, let me do another color. This area out here is basically repolarization. If we look at our action potential, it's out here. Now it's not real predictable how this change in repolarization will affect this. It's just known that it will change. You'll change the ST signal. You might depress it. You might make it larger. In any case, it's going to change. And if it changes, it means this changes, and it means this changed. So changes here, I'll just go ahead and draw it right on here. Changes here mean changes here, which means difficulty clearing potassium, which means decreased blood flow. So if you stress the heart, it starts contracting a bunch, need to clear out this potassium. If the potassium cannot be cleared because of decreased blood flow, it's going to decrease, or sorry, it's going to affect repolarization here, and you're going to see that as a change in the EKG. So the EKG is a diagnosis for decreased blood flow. One of the other things that can happen is if we slow this down considerably, then we can change how long it takes to go through this repolarization. And this is called the QT interval. Why do I care? The reason you care is because what I'm drawing now is I'm going to go out and start another, I'm going to go out and start another heartbeat. Next heartbeat. Well, there's kind of a timeout here, and it's called a refractory period. We'll write refractory period, but we'll say timeout. Refractory period. And this refractory period is basically there to make the heart rest so that the pacemaker has time to take over. So we're in timeout. As soon as we come out of timeout, this P wave, it's called the P wave, is set up by the pacemaker. And if you know what I'm talking about, then you know that that's basically atrial contraction. So we want to take a timeout, let the atria take back over and start the system back up. Well, if this is delayed out too long, we've still got cells. We've still got cells that are still depolarized. They haven't repolarized. So if you come out of this timeout and there are still cells elsewhere in the heart that are still depolarized, they will become the pacemaker. And that's a bad thing. So that's why often the QT interval is watched, because if the QT interval gets too long, it means there are cells that are staying depolarized. They might stay depolarized long enough through this timeout period that they actually take over for the atria, become the pacemaker of the heart. Okay, just to reiterate the points that I was making in this, I pulled this EKG off the internet. It's at www.ipej.org/0602/UCHIDA1.jpg, and I'll put this on the YouTube. But anyway, I just wanted to show that here is a person, and we'll just look at lead 1. who was pre-exercise, and it looks like a pretty normal EKG, P, QRS, and T. They were put on an exercise regimen or put on a treadmill or a bike cyclometer or something like that, and you can see that what was a normal ST segment has now inverted. It's below the baseline. Another thing to note is that the QT interval has extended. Over here the QT is maybe 7 little blocks. Over here the QT is upwards of 9 little blocks now, so it has extended the QT period. Upon recovery, everything is returned to normal. So again,